In this video, we are again looking at this aggregate loss model. Okay, so we want to find out the distribution of S from the distribution of N and the distribution of X. Unfortunately, the distribution of S is very difficult to find, except under some very special situation. Okay, so that's why here we consider an approximation. So the idea is very simple. We try to approximate the distribution of X by something discrete. Okay, so in general, this X can be a continuous variable. So we try to approximate X by a discrete distribution. Now, if N follows AB0 or AB1, so that means if N is Poisson, negative binomial, or there's zero modification, then we can apply Pench's recursion because this time X is discrete and N follows AB0, AB1. So we can use Pench's recursion in chapter 5 to find out the probability mass of S. Okay, so this is the idea. So now the problem becomes how to approximate a continuous X by something discrete. There are many methods around, okay? And in this chapter, we will look at one method, which is the so-called method of rounding. So to apply this method, we first need to fix H. Okay, so we call this H the span. Okay, so once H is fixed, we can define another variable. This variable is discrete, X prime. We define it in this way. So first of all, X prime equals 0, H, 2H, 3H, and so on. So X prime is a multiple of H. So X prime is a discrete variable. And the probability mass of X prime can be obtained from this formula. Okay, so essentially we are doing rounding. So X prime will be 0 whenever X is less than H over 2. And X prime equals H when X is between 0.5 of H and 1.5 of H, and so on. Okay, so this is how we can apply the method of rounding to define a discrete variable X prime. So you can see that if H becomes very small, then this X prime will have a distribution very close to the original variable X. So now let's look at one example. Okay, so for example, if I choose H to be 10, if I choose the span to be 10, then X prime equals 30 if X is between 25 and 35. Okay, so we define X prime through this probability. So the probability mass that X prime equals 30 will be fx of 35 minus fx of 25. As another example, suppose y, okay, so the random variable y, p, has a CDF like this. Okay, so it is actually a variable between 0 and 20. So part A is to discretize the distribution of this continuous variable using the method of rounding with a span of 10. Okay, so that means we need to define another discrete variable, call it y prime. Okay, y prime will equal a multiple of 10. So that means y prime can be 0, 10, 20, 30, and so on. And here we need to find out the corresponding probability mass. So for example, what is the probability mass at 0? So by the method of rounding, if H is 10, then y prime will be 0 when y, the original continuous variable y, is less than 5. So we need to plug in 5 in this CDF, and then we get 0.4375. And then y prime will be 10 when the original variable y is between 5 and 15. And we can compute this probability from f of 15 minus f of 5. Okay, so we plug in 15 and 5 in this expression, and then we get 0.5. Finally, y prime equals 20. So by the method of rounding, it will be 20 when the original variable y is between 15 and 25. But if you go back to this CDF, you can see this continuous variable y actually is bounded above by 20. Okay, so we only need to consider yp bigger than 15 and less than 20. So that means it is 1 minus f of 15, and this is 0.0625. Okay, and this is the end. So you can see if you add up these three numbers, you will get 1. So y prime is a discrete variable taking only three values, 0, 10, and 20. And this is a discrete variable we used to approximate this distribution. Of course, the approximation is not very accurate because this h is too large. If you choose a smaller h, y prime will take more values and y prime will be closer to the original y. Now, once we have this discretized y, we can look at another part. So suppose NP, the number of payments, okay, has a probability mass like this. We use the discretization in part A to calculate the probability that the discretized aggregate payment equals 0, 10, and 20. Okay, so the original aggregate payment will be given by YP1 plus YP2 plus YP3, YP4 up to YP/NP. But now we approximate YP by Y prime, by the discrete variable Y prime. So the discretized version of the aggregate payment becomes Y prime 1 plus Y prime 2 up to Y prime NP. So NP is still the same. Okay, so NP doesn't change, but each YP, the original continuous YP, is now replaced by this discrete Y prime. So now we try to use this S prime to approximate the original S. And I want to find the probability that this S prime equals 0, 10, and 20. So basically we can use Pension recursion because this N prime, if you look at the probability mass, is naturally a negative binomial distribution. So you can verify this by looking at the ratio Pn divided by Pn minus 1. It is actually 3 over 4, and you can write it as A plus B over N, with A being 3 over 4 and B being 0. So A is positive, that means it is negative binomial. And we know that for negative binomial, A, B are related to R and beta in this way. So because A is 3 over 4 and B is 0, so we can find out R and beta. So R is 1, beta is 3. So actually this NP variable is negative binomial, R is 1 and beta is 3. Okay, so we can use Pension recursion. So we first write down G0, the initialization of the recursion, which is P of NP, the PGF of NP, evaluated at F0. What is F0? F0 is the probability mass that this Y prime equals 0. Okay, and we obtain it in part A, which is here, 0.4375. Okay, and then this 1 minus 3t minus 1 negative 1 is the PGF of this negative binomial. Okay, and then we define this GK to be the probability mass of S prime, but only at a multiple of 10, because S prime must be a multiple of 10. Okay, so we do not define GK to be the probability that S star equals K, but S star equals 10 of K. K can be 0, 1, 2, 3, 4, and so on. So using Pension recursion, this GK will be given by this. How about F1? What is F1? F1 will be this, and this is F2. So we don't call this F10, we don't call this F20. We call this F1 and F2. So somehow you can think in this way. We can think of $10 as a unit. Okay, so now suppose we have another currency. So under this new currency, okay, 1 unit equals $10 in the original currency. So we treat 10 as 1. So we call this F1. This is F2. Okay, and that's why this is G1, GK. So rather than G of 10K, we call this GK. So we apply Pension recursion, and then we can get G1 and G2.